So my dad has a lesson that he likes to share with me on a fairly regular basis. And he says, John, if you're the smartest person in the room, then you're in the wrong room. And it's in this spirit today that I'm proud to kick off this year's Nanotechnology Capstone Design Symposium. It's very exciting to be demonstrating our work alongside some of the best and brightest that UW has to offer, which are all the brilliant and talented people that I'm proud to call my classmates. We have all come together today to show off our innovations to the problems that we believe are worth solving. I'm Jon Joel, and I'm thrilled to be up here with my project manager, Geoffrey Deignan, and my technical expert, Stephen Pynenburg. When we're finished, please come visit our booths and say hello to the three of us, as well as our process engineering expert, Alan Dorssers. Before I dig into the meat and potatoes of our project, there are a few people I would like to thank. First, I would like to thank our project consultant, Dr. Hani Aziz, as well as his students, Graham Williams, Sibi Seti, and Dr. Ising Vangsezi. We would also like to thank Dr. Irene Goldthorpe and Hadi Kali Hosseinzada for their contributions to the project. Also, none of this would have been possible without the support of Jen Coggin, Rossi Ivanova, Dr. Neil McManus, and Dr. John Sad. We'd also like to give a special thanks to Richard Barber for providing some materials and assisting with clean room access. We'd also like to give a thanks to our friends in Group 22 for sharing some of their materials with us. So thank you, and finally we'd like to thank our judges for being here, and thank you everyone for helping make today possible. So now we come to the problem that inspired the four of us to come together. Building owners everywhere are losing money. For instance, the building we are in right now is wasting the University of Waterloo $38,000 a year. That's enough to buy Dr. Neil McManus a new BMW 3 Series every year. On top of all of that, my favorite building, the QNC, is wasting the University of Waterloo $22,000 a year. And if that's not enough, on top of all of this, 6% of the electricity these buildings are still using comes from greenhouse gas emitting sources, such as natural gas and coal. The solution to both of these problems is to start producing clean, renewable power on site. And we're not the only ones who feel this way. There's actually a LEED credit for renewable power production on site. This means that on top of the savings from not having to buy this energy every year, buildings such as these could also receive a LEED certification and in turn a tax credit. Now, with problems as obvious and potentially lucrative as this, many people have tried to address the issue before. Wind turbines can go up, but wind is fairly unreliable, and wind turbines themselves have many moving parts and are therefore fairly maintenance intensive. Also, complaints are commonly heard about noise, and they can be fairly unsightly. Silicon solar panels can also be installed on building rooftops, but these too are fairly unsightly constructs. And even if building owners do decide to bite the bullet and cover the rooftop in solar panels and fit in wind turbines everywhere they fit, we still believe that we can squeeze more power out of these buildings by turning conventionally idle space into power-producing space. So what space do DC and the QNC have that is abundant and is sitting idle? Well, it's UW, so it's not parking space. We're really talking about the windows. 7 months ago, the four of us set out to make a better window. We wanted to allow windows to produce cash flow with a device that is transparent, scalable, and even green. This means that we chose to find a way to see through traditionally opaque components and fabricate them in a way that was almost entirely solution processed. More specifically, we're combining polymeric electron donors and fullerene electron acceptors for a bulk heterojunction style device using indium tin oxide and silver nanowires as the electrodes. For my mom and dad who have joined us in the audience today, I'm going to give a brief background on organic solar cells as well as some of the other tools in our engineering toolbox. After that, we're going to review the actual device components in our device, and we're going to show you the complete device and show you how our results stack up with our original project goals. So the word organic here does not actually refer to the overpriced tomatoes in the grocery store, but instead refers to molecules composed primarily of carbon and hydrogen. These carbon atoms want to have 8 valence electrons, but they only have 4. This means they need to share these other 4 electrons from other atoms. Hydrogen can share 1 electron with these carbon atoms. So if you have 4 hydrogens and 1 carbon, you can make the molecule you see on your top left. Carbon can also share 1, 2, or even 3 of its own electrons with another carbon atom. So if you have 2 carbons and 6 hydrogens, you can make the molecule you see in the top right. This chain can be extended almost indefinitely, and you can also create many interesting shapes, including rings. Now, if you have a long chain of carbon atoms with alternating double and single bonds, you create a phenomenon called conjugation, and that means the molecule will behave a bit like a semiconductor. The nice part about these materials is that we can often tune them to be excited by the color of light that we want. Often, this involves creating many ring-like structures in the material. These are regions that are called chromophores and give the materials their basic characteristic wavelengths of light that they absorb at, which is to say they give it a characteristic color. For this project, we aim to pick a material with a chromophore that absorbed very little in the visible spectrum of light, mostly absorbing in the infrared and ultraviolet portions of the spectrum. So there's a gap in energy between electrons in their lowest energy state, called the ground state, and their next available energy state. Unlike a classical energy barrier, you can't get this isn't like getting 3 of your buddies to push a stalled car up a hill. This is like getting all of your friends, taking a run at the car, and when your shoulders connect, the car hops to the top of the hill. The electron will only climb this barrier if it receives all the energy it needs at once. From the top of this energy hill, the electrons like to flow downhill, which creates electricity. Now that we know how to excite the electrons, we need to know how to capture them so we can make them do what we want. This is a lot like taking a classroom full of kindergarten students, filling them full of pop and candy, and trying to get them to walk in an orderly fashion down the hallway. For our purposes, this means preventing electrons from relaxing back to the ground state before we've put them to work. To do this, we add electron transport and hole transport layers. Holes are the vacancies left in the ground state when electrons are excited to a higher energy level and can be thought of as regions of positive charge. We don't want these holes to meet the electrons, so these transport layers pull them apart very, very quickly. After the electrons and holes have been separated, we want them to enter the circuit. To do so, we need 2 different conductive materials to serve as electrodes. Now that I've covered the fundamentals of how this type of device works, I want to take a look at the technologies that could bring these devices closer to commercialization. In research, these materials are often deposited with a very high degree of control using vacuum deposition methods. A common vacuum deposition method is thermal evaporation, which involves heating the desired material in a vacuum until it evaporates. After this, it will condense on the substrate in a highly controlled manner. Typical vacuum deposition methods are slow, expensive, and have low throughputs. In contrast, solution process methods have less uniformity and less performance precision, but the benefit is that these devices can be produced at scale with high throughput, and this reduces barriers to market entry. We actually use some very simple solution processing methods to fabricate our device. All of these methods have existing analogs for bulk fabrication. We bring in our glass substrate, pre-coated in indium tin oxide. Then we use spin coating to deposit our electron transport layer. On top of this, we can use spin coating to deposit our active layer. From there, we take a second flexible substrate and roll on our silver nanowires. After these have been sintered for better conductivity and adhesion, we spin on our hole transport layer onto the silver nanowires. Then we take our top flexible electrode, and it can be laminated on top of our glass half of our substrate. I would now like to introduce our project manager and team backbone, Geoffrey Deignan, to talk about some of the finer technical details of our project.
So 2 of the key design challenges to the fabrication of our device were making the electrodes look totally transparent to the human eye and finding a way to get good electrical contact between the 2 electrode surfaces. Indium tin oxide and other conductive metal oxides are very commonly used electrodes in organic solar cell research because they're all transparent and somewhat conductive. Unfortunately, these and the other conductive metal oxides tend to be very brittle and therefore inflexible, which prevents lamination as a scale-up process. We decided to circumvent this problem in the nano way by exploiting size as a physical property. We took conductive silver nanowires with a diameter of 90 nanometers and used them to replace our cathode materials. So to put 90 nanometers into perspective for you, this is about 1,000 times smaller than an individual pixel on an iPhone 6 Retina display. These nanowires form a mesh when deposited onto our top substrates as shown in the micrograph in the top left-hand corner of our slide. And we then sinter them for better electrical properties, such as reducing the resistance of the nanowires down to less than 20 ohms per square. We are also taking advantage of the flexibility of the silver nanowires by depositing them on our top plastic electrode, our plastic substrate. We are able to deposit the silver nanowires via roll-on methods onto our plastic sheets, which also enables reel-to-reel processing as a scale-up method. The next key portion of our electrode design is patterning. These devices need to be patterned onto the substrates as a method of failure tolerance. If one cell shorts on a pane of glass with many devices on it, it won't ruin the whole pane of glass. But if the entire pane of glass was just one single cell and it's shorted out by a single piece of dirt or debris, the entire pane of glass would be shot and the solar cell would be dead, which is a very expensive mistake. So for this project, we created a way to etch ITO patterns using the same photoresist found in the circuit board industry and without using hydrofluoric acid as a wet etch solution, which is quite a safety hazard. This method is cheap, safe, and reproducible. The silver nanowires were patterned using a stencil, which is also cheap, easy, and have an as high throughput. For our transport layers, we chose to use zinc oxide as an electron transport layer, and a conductive polymer called P.PSS is a hole transport layer. Both of these materials form very thin films when solution processed and can be deposited using spin coating methods. Zinc oxide and P.PSS were both chosen as carrier transport layers because they are almost entirely optically transparent and provide the necessary electrical contact to interface with the electrodes in active layer. Our active layer is a mix of two materials that form the bulk heterojunction. That is to say, this is the part of our device that actually absorbs light and generates electricity. For our electron donor, we chose to use a polymeric material called PDP-PT-PT, which is the thiophene copolymer, and the name is very long. This is a long polymer with each molecule containing many of the chromophores that allow electrons to be excited. We chose to use a polymeric approach instead of a small molecule approach, which is traditionally used in organic solar cell research, because polymers dissolve better in solution, making them much more readily adaptable to solution processing methods. Our electron acceptor was a fullerene material called PCBM, and this was chosen because of its transparency and solubility. The purpose of having both an electron donor and acceptor material is to pull excited electrons away from their corresponding holes, preventing them from recombining and losing the energy they captured from incident light. These two materials were deposited in a solvent and spun onto our glass substrates to have a thickness of about 200 nanometers. So again, to put 200 nanometers into perspective, this is about 200 times thinner than an individual strand of human hair. These two materials were chosen because of their absorbance spectra in the visible range. More or less, these two materials on their own have very little absorbance in the visible spectrum. Our laminate layer was chosen with a little bit of help from our friends Howard Campbell and Scott Gordon at DuPont and DuPont Asian Films. So DuPont sent us some samples of a plastic called Melanex to mount their silver nanowire electrodes onto. Melanex films are flexible and chemically stable substrates made of polyethylene naphthalate. The films even tolerate more than enough heat to allow us to thermally treat our silver nanowires right on top of them, making the Melanex films ideal for large-scale manufacturing. Taking all of these finer details into consideration, we are now able to discuss our prototype and its performance. With our device, we were ambitious, stepping way outside of our comfort zone to take on many different design challenges. In terms of fabricating the device we initially specified, we did come up a little bit short. However, we did validate all of our key design elements, including power production, transparency, and scalable fabrication.
So our transparency goal for this device was to allow 50% of light at every wavelength across the visible spectrum to pass through the device. We ran a simulation, and for our specified layer thicknesses, this device should have only absorbed a little bit in the red portion of the spectrum. To validate, we fabricated the device to spec as best we could and ran it through a UV-vis spectrometer. Though this device did not work electrically, its optical properties are still valid. If you take a look at this plot of the device's actual absorbance spectra, you can see that we actually had very good transparency. Though we absorbed a little bit more in the red than we would have liked, we actually believe that this could be improved by having a better annealing process, as this could lead to pi-pi stacking internally, which would lead to shifting this peak further into the infrared. This is also an issue that could be addressed with different photoactive polymers. As the chemistry catches up to the engineering, different polymers with different absorption spectra could be used. Another point of note is that not all exterior glass is totally transparent. Adding tints to these devices could make them more powerful, as well as more appealing to our friends in architecture. Our power goal for this device was to achieve a 1% power conversion efficiency. This would produce about 1 milliwatt of power per centimeter squared at peak solar intensity. Though state-of-the-art organic solar cells could produce as much as 10%, we had to make a design trade-off between transparency and efficiency. Based on the distribution of light in the solar spectrum, we picked a 1% power conversion efficiency. We fabricated this device using our solution process active layer, and then we swapped out our silver nanowire top electrode and used a more conventionally deposited, thermally evaporated aluminum layer to validate our electrical properties. This is opaque, but it did allow us to validate these properties. The JV curve for this device actually shows a fairly shallow slope, which shows a fairly high internal resistance, which means we have some room for improvement. Also, we only generated about 1/20th of the power that we wanted, but we did prove that our active layer and solution processing method of deposition work at a proof of concept level. Future work would involve optimizing the process parameters, such as the active layer thickness, the annealing method, and the ratio of donor to acceptor molecules, and we believe that this would improve the electrical properties by creating long-range order in the device in the active layer and reducing the electron-hole recombination.
A key design feature for scalable production was that we wanted to laminate the top transparent electrode onto a device. We approached this by taking a press and applying 12,000 pounds of force to push the two substrates together. We validated our lamination process in two ways. First, we just applied the force to ITO-coated glass and silver nanowire-coated plastic and checked to see if they adhered together with good electrical contact. The two substrates did adhere and were connected with a low resistance value of 250 ohms between the two substrates. In contrast, pressing together two non-flexible substrates, both ITO-coated glass, produced no electrical contact and they did not adhere. More importantly, we tested the silver nanowire substrate onto a standard Schottky solar cell using the same pressure and parameters. This device provided a relatively high voltage with a low current. The silver nanowires did indeed provide the desired electrical contact to the top electrode of the device. Because of the strong electrical contact, this device's process parameters could be modified to make the top electrode thinner and thinner until it is eventually no longer required. So we have shown that we can produce power using materials that are transparent and processes that are scalable. If we come to the challenge of turning wasted space into productive space, we have shown that the concept works and that the incremental optimizations we have discussed would make our design viable. We envision our design expanding the scope of solar power from rooftop and farm installations into everyday components in new building construction.
While our design and processes are different than existing solar technology, we don't actually have to reinvent the wheel in order to implement it. Using existing commercial channels and power control and distribution technologies, transparent solar cells could begin to complement and supplement their opaque counterparts in the very near future. This is a problem worth solving, and that's as clear as glass. Thank you.
Thank you very much. We have time for a few questions. The audience.
Yep.
You mentioned that the power production is 120, so you expected why
Yes.
that is the case?
Yeah, so we had some actual fabrication issues going on. For the actual device we tried to validate, we had the wrong ratio of donor to acceptor atoms in our active layer. It was also out in air for a while, and these aren't oxidatively stable yet. They're not stable against water and hydrogen, which also contribute. Further, our annealing process has not yet been optimized, which could also lead to less power production.
Okay, in other words, your expectation is right. There are some issues with your fabrication process.
Yeah, we actually believe that a 4% power conversion efficiency, I think that's produced in literature for transparent solar cells, could be achieved. So we aim for 1%, which seems to be very within reason. Yep.
So how did you design the silver nanowire layers to give the right transparency? How did it affect the transparency?
Yeah.
So how did it affect the transparency?
Yeah.
Compared to the rest of our device, they're probably one of the more transparent components. So if you remember the picture, it looked fairly green. The silver nanowires, depending on how thick you apply them, they tend to be up to about 80% transparent in some cases.
So did you guys have to do any optimization in terms of thickness of the layer?
Our silver nanowire deposition method, we didn't spend a huge amount of time optimizing that. We just checked under a microscope to see if it was actually formed a mesh to figure all that out. And that's just kind of, we're rolling with our hands for this type of step. So it actually worked out fairly well. You can see right through the silver nanowires, like optically, that's not, as a just qualitative test, they are very transparent on our substrate.
You didn't see any bee sculpture through silver nanowires?
Pardon me?
Any bee sculpture of light through silver nanowires? Because in otherwise it was 90 nanometers, right?
Yeah, when we
I
were,
expect a lot of bee sculpture happening.
when we made regions where they kind of clump together on some of our substrates, they look a little bit milky. So sometimes you can see a few milky ridges, which could lead to, which is a symptom of light scattering. But they're so small, and the transparency through them is actually quite clear. Yep.
What?
Yeah, okay. Do you think you could also improve transparency by using materials whose index of refraction matches better? Did you look at that?
We simulated that back in the sort of paper design phase. So that depends a lot on the different thicknesses of our layers. We didn't end up hitting exactly the layer thickness we simulated we wanted to use, just because of different spin codes we ended up using. But that's definitely something we were looking at.
Yeah. Yes.
Obviously, one of the keys for this is economics. Did you do some cost estimates about what you would need in energy return to make money on?
So we estimated what the device kind of fabrication cost is on a per square foot level. So on the prototype level, for the prices of materials that we were using at the scale, buying like quantities of 1 gram at a time, we're talking, this is on the order of $1,000 per square foot, which is pretty expensive. But we believe with scale up, you can actually bring this number quite down. So
there are other people also who are working on transparent organic solar cells.
Yep.
How does your efficiency compare to what has been quoted in the...
I said at some point, there's a projected literature value of around 4% for transparent solar cells as a power conversion efficiency. So we got 1/20th of 1%, which is far, far down from that.
Experimentally, do you know?
Sorry?
Experimentally obtained, not projected theoretical, but experimentally obtained values?
Experimentally obtained is 4%.
It's 4%. Okay.
All right.
Any further questions? Great, thank you very much.